In this session, let us discuss operations research, which is a scientific tool to our decision making. It consists of so many areas: queuing theory, game theory, simulation, linear programming problem, management programming, non-linear programming, etc. In the MSc course, in MSc program, the only course contains only 5 modules. First is linear programming problem. In linear programming problem, we can see that it is a technique to optimize the performance. The performance being cost or profit. When the performance is profit, we have to maximize the performance. So, for linear programming problem, we have to optimize performance subject to some constraints. These constraints and also these values are positive. Therefore, we can discuss this problem, linear programming problem, by means of an example, and we can define everything by means of this example. Okay. So consider consider the linear programming problem for manufacturing 3 products A, B, and C. So for these products A, B, and C, we have some restrictions, that is labor hours per day, per unit per day, per unit per day. It may be say 7 for a product and 3 for other and 6. Similarly, we can see that for raw materials, it has also a restriction, that is raw materials per unit required per pound is as follows. Raw material per unit per pound. It is also 4, 5, 5. And also for producing this product A, we have the profit per dollar per unit is as follows. Per dollar per unit is as follows. That is 4, 2, 3. Then there is a restriction in labor hours. That is, labor hours is maximum of 150 hours per daily for this labor hours required, and also the raw materials is also 200 pounds. Therefore, we can formulate by means of this data into a linear programming problem, such as if x1 units of a product is required for A, and for that of for B it is 3, and that is for C it is, for A it is x1 units, and for B it is x2 units, and for C it may be, we assume that it is x3 units. So we have to find the values of x1, x2, x3, that is, which maximize the profit. Maximize z equal to 4 into x1 plus 2 into x2 plus 3 into x3. Subject to some restrictions. Restrictions are, or constraints. Constraints are 7x1 plus 3x2 plus 6x3 should be less than or equal to 150. Similarly, for raw materials, it is 4x1 plus 5x2 plus 5x3 is less than or equal to 200. Again, number. So, x1, x2, x3 should be greater than or equal to 0. This first condition is called objective function, and the second is called constraint, and third is called non-negativity restriction. So, by means of this problem, we can formulate this problem into an LPP. Again, we can write this in the matrix form, that is optimize, that is here it is maximize z equal to 4, 2, 3, a row vector into x1, x2, x3. Subject to 7, 4 into x1 plus 3, 5 into x2 plus 6, 5 into x3. is less than or equal to the matrix 150, that is the constant matrix, and 200. And if we take capital X equal to x1, x2, x3, we have this problem makes the standard LPP. Standard LPP is linear programming problem is maximize z equal to Cx subject to Ax is less than or equal to B and x greater than or equal to 0. It is the standard linear programming problem. Then let us discuss how to solve this linear programming problem. One of the simplest method is by graphical method. Let us discuss how to solve a linear programming problem by graphical method. For that, consider the problem, minimize z equal to 40x1 plus 36x2 subject to x1 less than or equal to 8, x2 less than or equal to 10 and 5x1 plus 3x2 5x1 plus 3x2 greater than or equal to 45 and x1 x2 greater than 0. It is a standard LPP. So we can solve this by graphical method. For that we have to find feasible region, optimal region and then the optimal solution. Okay. So let us draw this by means of a line. Since first the last condition is non-negativity, that is x1, x2 greater than 0. So it becomes x1 and x2 are both positive, that is the first quadrant. Then we have the boundary, that is x1 is less than or equal to 8. For that we can draw the line x1 equal to 8. One, 2, 3, 4, 5, 6, 7, 8. So it is the point x1 equal to 8. So it is the line x1 equal to 8. Therefore, we have the region is boundary is x1 is less than or equal to 8. Similarly, we can find 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is x2 equal to 10. So it is the line x2 equal to 10. So again the boundary is less than 10. So we can check this. The next is 5x1 plus 3x2 greater than or equal to 45. 5x1 plus 3x2 greater than or equal to 45. For drawing that line, it is very simplest method is we write 5x1 plus 3x2 equal to 45, the line. Then put x on x2. When x1 equal to 0, we have 3x2 equal to 45, that is x2 equal to 15. Then put x2 equal to 0. When x2 equal to 0, 5x1 equal to 45, that is x1 equal to 9. So we can find the points. That is first point is 0, 15, 10, 11, 12. Then 0, 15. Then we have next point is 9, 9, 0. So we can join these two. This is the line 3x1 plus 5x1 plus 3x2 equal to 45. The boundary is greater than 45. So our feasible region is restricted to this area only. So it is the region bounded by say A, B and C. So among these 3 points we have to check which value this function minimize. For that consider A. We know this line 5x1 plus 3x2 equal to 45 So x2 equal to 10, we have 5x1 plus 30 equal to 45. That is 5x1 equal to 15. That is x1 equal to 3. Therefore, this point is 3, 10. A is the point 3, 10. Similarly, what about B? B is the point, that is the point of intersection of X. A is the point, we have A is the point 3, 10. And B is the point of intersection of x1 equal to 8 and x2 equal to 10. Then C. What about C? C is the point of intersection of x2 equal to 8. x2 equal to 8. So, sorry, x1 equal to 8. x1 equal to 8, we have 5x1 plus 3x2 equal to 45. Here, x1 equal to 8. So, for 40 plus 3x2 equal to 45 gives 3x2 equal to 5. So, x2 equal to 5 by 3. So, C is the point 8, 5 by 3. Then, we can find for which value this function has optimum value. At A, z equal to 40 into 3 plus 36 into 10. That is 120 plus 360 gives 480. At B, 40 into 3 plus 36 into 10 gives 120. Sorry. At B, 810. At B, it is 810. So, 40 into 8 plus 36 into 10. It is 320 plus 360 gives 680. Then at C, x1 equal to, C it is the point 8. So 40 into 8 plus 36 into 5 by 3 gives 320 plus 60. That is 380. So we have three values which minimize this function. Z equal to 40x1 plus 36x2, you know it is 380. So at C we have the minimal value. So it is optimal solution is x1 equal to 8 and x2 equal to 5 by 2. This method we can solve any linear programming problem by graphical methods. Then let us solve by simplex method. So, simplex method we have to apply so many technique, but every technique may be illustrated by means of this following example. Okay. So, solve the linear programming problem using simplex method. Yes. Maximize z equal to 3x1 plus 2x2 subject to the condition minus x1 plus 2x2 less than or equal to 4, 3x1 plus 2x2 less than or equal to 40 and x1 minus x2, question should be carefully right, less than or equal to 3 and x1, x2 greater than or equal to 0. We have seen that it's a maximization problem. A standard maximization problem is subject to maximize. If the problem is given to be minimized, we can multiply the objective function by minus 1, then minus z we have, then finally we can. So, if the problem is given, objective function is given to be minimization, we can make this as maximization by multiplying the objective function by minus z. Here it is the maximization problem. And second condition is all the signs are less than or equal to And also we can see that the constants are always positive. If the constant is negative, we have to multiply just similar to the objective function by -1, we get the constants terms should be positive. Then here it is less than or equal to. So we have to introduce another variable is called slack variables, adding a positive number. Say x3 as one of the slack variable, we get -x1 plus 2x2 plus x3 equal to 4. Second is 3x1 plus 2x2 plus x4 equal to 14. x1 minus x2 plus x5 equal to 3. x1, so we have had more 3 variables. So we have x1, x2, x3, x4, x5 greater than or equal to 0. Maximize z. So it is the second stage. We introduce slack variables in order to make this less than inequality to equality. Then let us see the first table. For the first table, we have 5 variables. So we have to introduce 5 plus 3 columns. By drawing more and more tables, you are aware of this, how to construct this table. Okay. It's very simple. Then here Cj, and here xb. xb means vectors in the basis. Then here we write all the variables. That is, first variable is x1, second variable is x2, third is x3, x4 and x5. Then constants. Then we can write the coefficients corresponding to x1 in the objective function, that is 3, 2. These are all slack variables, so we assign the price 0. Okay. Then xb, we have to make basis vectors as so that matrix should be identity matrix. So basic variable is the variables assigned to identity matrix. So identity matrix, we have this x3. x3 means x3, then we can see that it is this is -1, 3 and 1. Here 2 minus 1. Then for x3 it is 1 0 0. For x4 it is 0 1 0. For x5 it is 0 0 1. We have seen that these 3 vectors forms the identity matrix. So this is here first, therefore it is x3, here x4, here x5. Okay. Then what about the constants? We see that constants are 4, 14, then 3. Then corresponding to this basic variables, we can assign the price, that means CB. Cost assigned to the basic variables. Basic variables are the variables assigned to the identity columns. Columns of the identity matrix. Again we see that corresponding to x3 here 1, x4 here 1, x5 here. Then CB is the cost, that is 0 0 0. Then we have one more row. Okay. This row is called profit value, Cj bar. Profit value. Profit is here, we have Z is -3. 3 minus etc. So again we can see that 3 minus everything is -1 into 0. Cj is obtained by Cj tilde. Cj bar is obtained by Cj minus Zj. What is Zj? Zj is the x1 product into that cost, x2 product into that cost, x3 product into that cost. So we have minus 1 into 0, 3 into 0, 1 into 0 gives 0. So it is 3. Similarly here it is 2. Again we can see that for identity matrix that value is 0. So the maximum value is also 0. Okay. This is the initial solution. But here these values are basis is x3, x4, x5. We require the value of x1 and x2. So we have to improve. How to improve the solution? First of all, our aim is maximization. So maximum profit should be selected. So 3 is the maximum profit value. So that we have to enter x1 into the basis. So x1 is entered into the new basis. And what is the vector to? Whenever we enter a basis vector, we have to remove another vector. So what vector we have or what variable we have to be removed is obtained by the minimum ratio method. In minimum ratio method, the constants by this xij. But provided if it is negative, we assume that is infinity. So we can consider only positive values for this value. It is very important. We have neglect the values in the column for which the values are less than or equal to 0. So we have to find the minimum of 14 by 3 and 3 by 1. What is the minimum? Minimum is obtained by 3 by 1. 3 by 1. So this element is called pivot element. This element is called a pivot element. By means of this pivot element, we have to make this x1 as the identity column. For identity column, here we have this is 1 and this 2 should be 0 by elementary transformation. How we will say? That is from R1 plus R3 minus 1 plus 1, it is 0. Okay. The next is 3. 3 may be 0 by means of this 1 only if R2 minus 3 R1. R2 minus 3 R1. R1 plus R3 and R2 minus 3 R1. So, even in order to avoid this space, shortage of space, we can remove this also. So, x3, here x5 instead of x5, we have removed x5. x5 is removed from the basis. And which vector enters? x1 enters. So, instead of x5, we have x1. Okay. Then there is no change in this. Then what about this? R1 plus R3. R1 plus R3, again here these values are 0. Then we can assume that all the vectors in the basis, the column should be 1, 0, 0. So x3 it is 1, 0, 0. x4 it is corresponding to x4 here 1 and the remaining 0. For x1 it is 1, 0, 0. Then R1 plus R3. R1 plus R3 we have to, this is x2, R1 plus R3. Yes, 2 plus minus 1 gives 1. Okay, 2 plus. Then here 0 plus 0 it gives 1, 0. There is no change. x5. x5 0 plus 1 gives 1. And also here 4 plus 3 gives the constant term 7. Here then R2 minus 3 R1. R2 minus 3 R1. 2 minus 3 minus of minus 3 5. Then here for x5 R2 minus 3 R1, that is we gives R2 minus 3 R1 gives minus 3. And 14 minus 9, that is 5. Then the last column there is last row there is no change. So we get x5 corresponding to x5 we have the second table is 0, 1, 1, 0, 7, 0, 1, 7. Then 0, 5, 0, 1, minus 3, 5. Then 1, minus 1, 0, 0, 1. Yes, 3. Here the constant terms are also changed by this linear transformation, this pivot operation. Okay. So the method is, first of all we have to find, if the problem is for optimization, that means maximization, we have to find the greatest value in the profit value. Corresponding to that value, we have to check which value is optimal. Minimize. So minimal xi minus this Cj constants by this xij, provided this xij should be greater than 0. For that we have to select which is the minimum value. We see that it is the minimal value, that element is called a pivot element. Then we have to make all the two elements should be 0 by means of elementary transformation, that is R1 plus R3 and R2 minus 3R. From this table again we have to find this value also, Cj. Cj is changed because this x1 constant coefficient of x1 is here 3. So here we have change in this value also. It is 0. Then here 2 minus 1 into 0, 5 into 0 plus minus 1 into 3. That is 2 minus 3, 2 minus minus 3 gives 5. Again here minus 3, for x5 it is minus 3. And also for the cost, it is 0 into 7 plus 0 into 5 plus 3 into 3, that is 9. So we improve the objective function, is 9. Then the third is, it is the second table. Then we have come on to the third table, because there is, we have to optimize this value also. Here Cj is Cj tilde is positive for x2. So this x2 should be entered into the basis. x2 entered into the basis. When this x2 enter, we have to remove a vector in the basis. Let us examine. Here the minimum ratio rule we can apply. Minimum ratio rule, here the value is 1, so it is 7 by 1 and also 5 by 5. Here we cannot take because the value is negative. So we get the minimum value is 1. 1 is corresponding to this value. Therefore, this 5 is the pivot element. 5 is the pivot element, and it is obtained by minimum of 7 by 1 and 5 by 5. Then x2 enters. Therefore, you see, x2 enters and which vector removed? x4 removes. x4 removes. So x4 removes and x2 enter. Then the coefficient is also changed to 2 Cb, the cost associated to this. Then our aim is, this must be 1 and the remaining should be 0. So what is a pivot of transformation? We know R2 into 1 by 5, R2 into 1 by 5, and also R1 minus 1 by 5 into R2. Then R3 plus 1 by 5 into R2. Yes. When we subtract 1 by means of this 5, that is R1 minus 1 by 5 into R2. R1 minus 1 by 5 into R2 gives here 0. And also here R3 plus 1 by 5 into R2 gives here 0. So this vector becomes here 0, 0. Okay. Also we know x3 is in the basis, x2 is in the basis, so here 1. x2 is in the basis corresponding to here 1 and x1 is in the basis. So 1 0 0, x2 1 0 0, x3 1 0 0. We have the identity matrix. So corresponding to this identity matrix we have the profit is also 0. Then we can find this x4, the x4, x5 and this constant term by means of this transformation. So R2 into 1 by 5. R2 into 1 by 5 gives 1 by 5. 0 into 1 by 5 gives 0. Then, sorry, R2 into 1 by 5. So R2 into 1 by 5 gives x3 is 0. Here, x3 is also basis. So here 1 by 5 minus 3 by 5 minus 3 by 5 and here 5 by 5 gives 1. Okay. The next transformation is R1 minus 1 by 5 into R2. Sorry. So the matrix is changed. R1 minus 1 by 5 into R2. It is R1 minus 1 by 5 into R2 gives last. Here the elements are 1 minus 3. Okay. Here 5. Lastly we can change. Then here R1 minus 1 by 5 into R2. R1 is here. X4 we have 0. 0 minus 1 by 5. That is we get minus 1 by 5. Minus 1 by 5. Then R2 minus this gives 3 by 5. Okay. Then here R3 plus. Here the value is 7. Then, so 7 minus 1, that is 6. Here 0 0 1, 0 0 0 1, 0 minus 0 plus 1 by 5 into R2, 1 by 5. Then 1 plus 1 minus 3 by 5, that gives 2 by 5. And also 3 minus 1 by 5 into, that is 3 minus 3 plus 1 by 5 into 5, R2 5. We get 3 plus 1, we gives 4. Here 1 minus 3 by 5, 1 by 5. It is the second table, but we have to find this cost also. Cost is here 2, 3. Therefore, here 3 into 1 by 5 plus 2 into 1 by 5, that is 1, 5 by 5, that is 1. So, it is minus 1. Here also we get minus 1. Here also we can see that is 0. So, there is no positive profit. Therefore, it is the optimal solution. And the optimal value is here 2 into 1 plus 3 into 4. That is 3 into 4 12 plus 2, that is 14. Hence, we can read the solution from this table. This is the optimal solution. And x2 equal to 1 and x1, x2 equal to 1 and x1 equal to 14, x1 equal to 4 and also z equal to 14. So, by means of this simplex table, we can solve an LPP. We have here 3 tables. By the shortage of space, I have adjusted in 1 table. Okay, but here we see that there is a matrix XB. XB is the vectors variables in the basis, that is x3, x2, x1. Then first we take x1, x2, x3, x4, x5. It is Cj. Cj is the cost associated. It is the constant term. Then we find for maximization problem maximum value of Cj bar. Cj bar is obtained by Cj minus Zj. Cj is this cost, Zj is the product of this. Then we checked it to be enter into the basis is the maximum value of this Cj bar. Then the vector to be removed is selected as the minimum ratio of the constant by that by these values in the vectors columns. Then that value should be greater than or equal to greater than 0. Therefore, that minimum element is called a pivot element. Then we can find the elementary transformation by so that these vector variables corresponding to the vectors have basically has a vector such that it is the identity matrix. So for correcting that element, we have elementary transformation we can design. Okay. Then from this table, the final table that is the optimum table, we can read the solution as x2 equal to 1, x1 equal to 4 and z is obtained 2 into 1 plus 3 into 4. 2 into 1, 2 plus 12, that is 4, that is z equal to 4. It is the method of finding solution by simplex method. But sometimes it cannot be possible. In that method, the situation, we have two methods. We have to discuss two methods. One is a bigger method and another is two-phase method. In bigger method, we consider all the variables, all the cost for that same, and also we introduce artificial variables so that this basis matrix becomes identity and the cost associated to that is m, where m is a very big value. So let us see how to solve a problem by bigger method. Use bigger method, maximize z equal to minimize z equal to 4x1 plus 3x2 subject to 2x1 plus subject to 2x1 plus x2 greater than or equal to 10, x1 plus x2 greater than or equal to 6, minus 3x1 plus 2x2 less than or equal to 6, x1, x2 greater than or equal to 0. Here, these two constraints are greater than. So we have to make these constraints to equality. We have to subtract a positive quantity. That variable is called a surplus variable. If we add a positive quantity, that is called a slack variable. Okay. So 2x1 plus x2 minus x3 equal to 10, x1 plus x2 minus x4 equal to 6 minus 3x1 plus 2x2 plus, here it is less than, so plus x5 equal to 6. So we have a problem. Then just as the simplex method, we have to construct a table so that the cost associated to these x1, x2 are 4 and 3, x3, x4 and x5 are 0, and we have only, if we write, it is in the matrix form 2, 1 minus 3 into x1 plus 1, 1, 2 into x2 plus minus 1, 0, 0 into x3 plus 0, minus 1, 0 into x4 plus 0, 0, 1 into x5 equal to 10, 6, 6. Here we see that the only one column for identity matrix is obtained, that is 0, 0, 1. So we have to introduce two artificial variables, that is x6 and x7. So x6 is, so it is plus x6 into 1, 0, 0 plus x7 into 0, 1, 0. So it is the standard form. Okay. So we introduce two artificial variables x6 and x7. Then let us start a table. Again, whenever these artificial variables are removed, then we can neglect that column also. So here Cj, then here xb. We see that xb, we have three vectors. One of them is x5 and x6 is the first vector, x7 and last is x4. Then x1, x2, x3, x4, x5, x5, x6, x7 and the constant. So here for xb we have x6, x7, x4. Here cb. Yes. For x1 it is 2, 1, minus 3. For x2 it is 1, 1, 2. Then for x2 it is. Then for x3 it is minus 1, 0, 0. x4 it is 0, minus 1, 0. x5 it is 0, 0, 1. x6 it is 1, 0, 0. x7 0, 0, 1. Cost is 10, 6, 6. Yes. That is the, then here cost. Cost is 4, 3, 0, 0, 0, m. This is the first initial table we have. Then here CB. CB is here. It is x6. It is m. x7 also m. x4 it is 0. Cost is 0. Then we have to find the profit value Cj bar. For the table 1, we have to find the profit value. For that, it is 4 minus 3m. 4 minus 3m. Here, 3 minus 2m. 3 minus 2. Then here x3 it is 0 minus m, that is m. Here also m. Then it is x5 it is also 0. Then 5 it is 0. Then for this x6 is basis, x7 is also basis. Then here the value is 10 plus 6, 16 m. Objective function is 16. Yes. Here, the objective function is minimization. So we have to find the least value in the profit. Minimization we have to find least. So corresponding m is very large. It is the least value 4 minus 3m. So we can take this is least. It is x1 enters into the basis. X1 enters into the basis, and we have to find the vector, which vector to be removed. For that we have to find the minimum ratio rule. Minimum of 10 by 2 and 6 by 1. Yes. That is 5. Therefore, yes, that is 5. Therefore, it is the pivot element. 2 is the pivot element. By means of this pivot element, what are the pivot operation? We have the operation is, first of all, we have to make this as 2. 2 makes 1, it makes 0, it makes 0. So, 2 R1 into 1 by 2. This last. Then, R2 minus 1 by 2 into R1. R2 minus 1 by 2 into R1. Then, R3 plus 2 by 3, 3 by 2 into R3 plus 3 by 2 into R1. Yes. By means of this transformation, we have R1 into 1 by 2 can be lastly found. Then R2 minus 1 by 2 into R1. Then again we can see that the variables in the vectors, that is 1, 0, 0, then x7, it is this. We removed this vector. x6 is removed from the basis. So we can replace x6 by x1. Okay. Then corresponding to x1, we have at least last. Then x1, x7 is in the basis and x4 is in the basis. x4, x5, x5. x5 is in the basis. Yes. Then R2 minus 2 R1 gives, here 0. Then for this x2 it is R2 minus 1 minus 1 by 2 gives 1 by 2. Here 0 minus 1 by 2 gives 1 by 2. And minus 1, there is no change. Then we have 0, then here 0, it is x7, it is 1. 7 it is 1. Then 6 R2 minus 1 by 2 into R1. 6 minus 1 by 2 into 10, that is 5, that is 1. Similarly, R3 plus 3 by 2 into R1. R3 plus 3 by 2 into R1 gives minus 3 plus 3 by 2 into 2. That is minus 6 3 by 2 into 2 instead of 2 we have, it is 7 by 2. Then here it is minus 3 by 2 on simplification. And also here 0, 1, 0, here 1. Then here we can see that 6 minus this, 6 plus 3 by 2 into 10 gives 3 plus 6 plus 15, 21. For this, lastly we can change. So 2 by 2, 1, 2 by 2, 1, 1 by 2, minus 1 by 2, 0, 1 by 2, 10 by 2, 5. So we have the new table with these values is 5, 121 and the bases are x1, x7, x5. Then we can find the profit value also. For profit value, we have m by 2 plus m by 2. So it is x1 is in the basis, so it is 0. Then it is x1 is 0. Then also it is, we can see that is 0. Sorry, it is m by 2 plus m by 2. Sorry, x1 the cost is 4. Yes. So 4 into 1 by 2, 2. Yes, 3 minus 2, 1. 1 minus m by 2. Similarly, we have here the cost is 2 minus m by 2. The other cost is m 0, 0. Then the last is also changed. What is that value? We have 4 into 5, 20 plus m. But here also we have two values of negative value. 1 minus m by 2 and 2 minus m by 2. Comparing 1 minus m by 2 and 2 minus m by 2, the least is 1 minus m by 2. So we take this as the vector to be entered into the basis. So x2 enters into the basis and we have to find which vector to be removed. That is the minimum of this one, that is 5 by, minimum of 5 by 2, 5 by 1 by 2, that is 5 into 2. And also 1 by 1 by 2, that is 2. And 21 into 2 by 7. So the minimum value is corresponding to this value 2. That is 4. 2 it is. Yes. So this is 1 by 2 is the pivot element. According to that, we have to find the pivot operations. What is the pivot operation? We have to make this as 1 and these two are 0. For that, we have R1 minus R2 and R3 minus 7 R2 and also R2 into 2. R2 into 2 gives 1. R1 minus R2 gives 0. Then R3 minus 7 R2 gives 0. So we have to make this as 1, 0, 0. So the operations are R1 minus R2. R1 minus R2 gives R1 minus R2. This gives minus 1 by 2, minus 1 by 2, that is minus 1. So it becomes minus 1. Also R1 minus R2, that gives, it gives 1. And also 0, there is no change. 1 by 2, there is no change. This is only change. This here also 0 minus 1, it is minus 1. Then 5 minus 1, that is 4. It is very important. Also, then R3 minus 7 R2. R3 minus 7 R2 gives, R3 minus 7 R2 gives it is 0. It is also last. It is 0. Then this element R3 minus 7 R2. R3 is minus 3 by 2 minus 3 by 2 minus 7 by 2. That is minus 10 by 2. That gives minus 5. Okay. Then next is minus 5. Then it is here minus 1. And x5, it is x5, it is minus 5 minus 1. It is 1. There's no change. There is 0. Then here 21 minus 7 R2 21 minus 7, we have 14. Sorry, 21? R3 minus 7. Yes. 5, 121, 40. Yes. Then the last is we have to multiply R2 into 2. R2 into 2 gives 1, 1 minus 2, 2, 2. Then we can find this initial value, this profit value. There is a correction in the book, so you have to replace this value. So the solutions are x1 equal to 1, 1 by 2 minus 1, 1, 0, 1 by 2, etc. Then since there is, since here, yes, x7 is removed and we replace x2. x2's the coefficient is 3. Okay. So there is no need for this x5 and x7. So we can delete these two. And the final solution is xb is x1, x2, x5. So we have to check whether it is the optimal solution. For that, x1 is in the basis, so it is 0. x2 is in the basis, so it is 0. x5 is in the basis, so it is 0. Also, 3 is 0. Minus 4 plus 3 gives 1. And also here we get 2. This is the final solution excepting these two columns. So from this we can read the solution as x1 equal to 4 and x2 equal to x1 equal to 4, x2 equal to 2 and z. What is the z? Z is 4 into 4, 16 plus 6. 16 plus 6, it is 22. So it is the bigger method. In bigger method, we have to assign the cost, capital M, which is a very large quantity. Then as it is a minimization problem, we have to find the least value of this. And that vector to be enter into the basis. Then we have to find which vector to be removed from the basis. For that the minimum ratio is applied. Then we can find the pivot element and also pivot operations. By means of these pivot operations we can find the solution. Then whenever these artificial variables are exempted, we can delete that columns also. Whenever. So we get this x1 equal to 4, x2 equal to 2, x5 it is not a basic solution, so it is 0. Yes, and the optimal value is 22. So we are right. Bigger method, simplex method, graphical method. The last one is two-phase method. In two-phase method, how we solve a problem. So in page 32 there is a correction. So I explain that method. And in two-phase method, let us discuss a problem that is, say, minimize z equal to minus 3x1 plus x2 plus x3 subject to x1 minus 2x2 x1 minus 2x2 x1 minus 2 x2 yes. Three x1 plus x2 plus x3 subject to x1 minus x2 is less than or equal to x1 minus 2x2 plus x3 less than or equal to 11, then 4x1 plus x2 plus 2x3 greater than or equal to 3, and 2x1 minus x3 equal to minus 1, x1, x2, x3 greater than 0. It is a minimization problem such that x1 minus 2x2 plus x3 less than or equal to 11. So we can apply slack variables so that this becomes x1 minus 2x2 plus x3 plus x4 equal to 11. Okay. Second is 4x1 plus x2 plus 2x3 minus x5 equal to 3 is greater than. Then here the variables are, the constant term is negative, so we can apply minus sign so that minus 2x1 plus x3 equal to 1. Then we have the table. x1 into 1, 4 minus 2 plus x2 into minus 2, 1, 0 plus x3 into 1, 2, 1 plus x4 into 1, 0, 0 plus x5 into 0 minus 1, 0. So here equal to 11, 3, 1. In this problem, we have seen that corresponding to x4 we have only one column with 1, 0, 0. But the two columns should be arranged so that we have to introduce artificial variable. Here x5, so we can apply x6 and x7. But here we apply two-phase method. Two-phase method, we assign, for the first phase, we assign the price 0 to all variable except artificial variable. So the objective function becomes minimize z equal to only m into x6 plus m into x7, subject to this. So we can apply we can start the first table. First table, just as the previous case, we can here Cj, here Xb, and here the prices are 0, 0, 0. Here we have to introduce x1, x2, x3, x4, x5, then x6, x7 and constant term. Here for this only 0. Then you can complete the answer. That is x1 it is 1, 4 minus 2, and x2 it is minus 2, 1, 0. x3 it is 1, 2, 1. x4 it is 1, 0, 0. x5 it is 0, minus 1, 0. Then x6 it is 0, 1, 0. x7 0, 0, 1. Then the last is constant term. Constant term is 11, 3, 1. Okay. Then here, just as the previous case, the coefficients are, here the variables are x4, x6 and x7. The cost associated to the matrix are, here we assume it is 0, here it is m, and here it is also m. Then, just as the previous case, we can find Z, C, J, tilde. Not m, this one. Here also one more, in two-phase methods. In two-phase method, we assign the price for one for these artificial variables, and just as the previous case, we can calculate this is a Cj bar. Cj bar is minus 2, 0 minus, that is minus 2. Here also x2 it is 1 plus 2, that is 1. Then here 0 minus 2 minus 3, 1 into 0, 2 into 1, 3 into 1, that is minus 3. Here for x4 it is 0, x5 it is 1, then x6 is in the basis, x7 is in the basis, and the remaining. Yes. Then we have to find that it is a minimum cost. So minimal is this. So we can this x3 enters into the basis and one of the vector to be removed. That is we can apply minimal ratio rule, and that we can see that is the minimal. Then just as the previous case, we can, the pivot operations are R1 minus R3 by means of this element, and R2 minus 2R3. We can find the improved solution. At a stage, we can remove these x6 and x7 and obtain the final solution after it. Yeah, whenever these two remove, x6 and x7 are removed, we can come on to stage 2, phase 2. In phase 2, what happened? In phase 2, we put the variables, the original cost for this. Original cost means, original cost is minus 3, 1, 1. And for x4 and x5 it is 0. And we improve the solution and we get the final solution. That is the two-phase. So, we have studied linear programming problem. First is formulation, then graphical solution, simplex method, and also a two-phase method. In two-phase method, we have two phases. First phase, we have to assign the price 1, 1 for artificial variable and the remaining for 0, 0. When the artificial variables are removed, we are come on to phase 2. In phase 2, there is no artificial variable. We introduce the, we start with the coefficients as the original constants. Then maximize and minimization problem can be solved. Again, sometimes some problems arises. If is this objective function, we have to find an vector to be entered is say x1, but all the coefficients are negative, we cannot find a vector to be removed from the basis. Such a situation, we say that the solution is unbounded. That is, the objective function is no, the profit value is not optimal, but also there is no choice for deleting base vector to be variables to the from the basis. Similarly, we have a tie-up. Sometimes the ratio is the minimal ratio is 1 by 2, 1 by 2. In that stage, we trial and error method, which is arbitrarily any one of them. And sometimes this value in this last column, constant term, suppose say 0, 0, say 5. So there is a degenerates, that is the basic variables are 0, we say that the solution is degenerate. So unbounded solution, degenerate solution, and also optimal solution, basic feasible solution, etc. we are defined by means of these problems. Okay, thank you.